So onward and upward, the discovery of benzene. So Michael Faraday, you'll recall from how many coulombs per equivalent. So back in his day, they had a lot of gas lighting, and in coal tar gas, there's this compound, and he determined that its carbon to hydrogen ratio was 1:1, and he named it bicarbonate of hydrogen. And about 9 years later, another fellow determined it to have a molecular formula to be C6H6. So like I always like to do, 6 twice is 12, 2 more is 14. 14 minus 6 is what, 8? Divided by 2, 4. 4 degrees of unsaturation. Probably 3 double bonds in a ring, which you probably already know. Now there's other compounds that have a low carbon to hydrogen ratio, and these had a pleasant smell. So they were classified as aromatic. Think of the word aroma. Sometimes people like to grind their own coffee beans right before they make their coffee because it's more aromatic. Well, we're going to learn that aromatic means something else, and we'll have some rules for it. So there was a fellow by the name of Kekulé, and they had a hard time figuring out what the structure of benzene was. You know, they didn't have mass spectrometry, they didn't have NMR, they didn't have X-ray crystallography. Basically, they had a combustion analysis, and he was having a hard time trying to figure this out. Now, my predecessor used to do a lot with all the constitutional isomers of C6H6 and monochlorinated or dichlorinated. And that's one thing they could do. They could make chemical derivatives and look at melting points and isolate different pure substances. So if I have 1,2-dichlorobenzene, there's only one isomer of that. So everything they knew at the time, so this is kind of an exaggerated drawing, where I made the sigma bonds longer than the pi bonds, and these would be both 1,2-dichloral, but if this was the case, this would be an isomer of this one. It'd have different properties, and they weren't observing that. So Kekulé, he was troubled. The story goes he went to bed at night, and he had this dream where a snake grabbed its tail and rolled after him and tried to bite him. No, that last part's a lie, but it's funny to imagine a snake that would do such a thing, right? And he woke up and he said, I've decided what the problem was. How many different places could I put the chlorine, and how many different structures could I have? So that's one of the things they had to work with. They can make the mono substituted benzene, they'd make chlorobenzene, and it's one compound. Now, if I had all these different isomers of C6H5, sorry, I can only come up with 2 on the fly. I should have looked at those old notes. Yeah, it's a waste of time. So they were having trouble with that. Kekulé had his dream, and this is what they come up with for benzene. So here we see sigma bond is longer than a pi bond. We look at butadiene. So these were real exaggerated, but nowadays we can freeze out some benzene and do an X-ray crystal structure and see that all the bonds are equal in length. And since chemists are lazy, as you already know, we get tired of drawing all these pi bonds, and so a lot of times we'll draw our hexagon and put a circle in it to represent benzene. Benzene is actually a resonance hybrid between these two, and we can draw those bonds jumping there, those jumping there, those jumping there, and we have that structure. Then of course, so we could probably do something with the Heisenberg uncertainty principle and say we really don't know where the double bond is. The CC bond length in benzene are shorter than a typical single bond length, yet longer than typical double bond lengths. And you might have did bond order in Chem 2. So we draw a resonance structure. So we see a perfect 120 bond angle there, and we think about all these are unused p orbitals. So there's an sp3 hybridized orbital there, an sp3 hybridized there, an sp there. And so what you learned in Chem 2 or Chem 1, I think, that a pi bond is the parallel overlap of two atomic p orbitals. And here's the nice space filling model of benzene, and everything's identical. And so you should know this about pi bonds. Each sp2 hybridized carbon in the ring has an unhybridized p orbital perpendicular to the ring that overlaps. These all overlap, so the electrons are free to move around. We'd say they're delocalized, those electrons, free to move around. So we can just go back to the alkene chapter, and we saw that a double bond is a functional group, has known chemistry, likes to undergo addition reactions. And we just pulled out some bromine, put it in some solvent, we'd see no reaction occur. Now, if we add a catalyst, we see a reaction, but it's not the anti-addition that we saw from the alkene chapter. We don't form any of this. We form this substitution business. When bromine adds to benzene, a catalyst such as a ferric bromide is needed. The reaction that occurs is a substitution of a hydrogen atom by a bromine. See, this hydrogen went away, stuck a bromine on there. We had one left over because we had Br2, so we get this as a product. And we don't see this. And so before today, you'd say, oh, I know how to add Br2 across the double bond from the alkene chapter. That does not occur. Don't observe that. Benzene does not have the predicted heat of hydrogenation. So we just saw from the last chapter, Zadov's rule and conjugated double bonds can lower heat of hydrogenation. The observed heat of hydrogenation is negative 208 kilojoules per mole, and that's a difference of 151 kilojoules. This difference between the predicted and the observed value we call resonance energy. So how do we get to that predicted? Well, here's a double bond. Let me just go 120 times 3 if I got 3 of them. My calculator says 360. That's pretty close. So here's what it's predicted. Well, maybe because it's going through this. Here's some resonance energy. Here's what we observe when we hydrogenate benzene. So we say this is how much this is stabilized by resonance. Annulenes. Cyclobutadiene, 4 carbons, we just call it a 4-annulene. Benzene, 6 carbons, we can call it a 6-annulene. And then some of these other things. I won't hold you to name any of these annulenes. We got better use of our time here. But what is an annulene? They're hydrocarbons with alternating single and double bonds. And you should get excited about that and say they're all conjugated. And we saw in the last chapter that conjugation normally adds some stability, and we just went over how benzene is so stable. And that's one of the characteristics of something being aromatic. Jonathan?
Do the annulenes have to be in a ring?
It has to be a ring, I believe. So here is, good question, Jonathan. All cyclic conjugated hydrocarbons are not created equally. That's not what it says. But they were thought to be all proposed to be aromatic. It has nothing to do with the smell. It has to do with stability. And so there's some weird things going on here. Cyclobutadiene is so reactive that it dimerizes before you can isolate it. That means nobody can put this in a bottle. Now, benzene can be put in a bottle, and so these don't undergo that resonance. So this thing is a weird thing. Cyclooctatetraene adds bromine readily, just like a normal alkene. So clearly these cyclic conjugated structures don't possess what benzene has going on. So now we're going to go into what does it mean to be aromatic. Structures must be cyclic with conjugated pi bonds. Well, that last slide, these were all cyclic and had conjugated bonds, so there must be more requirements. Each atom in the ring must have an unhybridized p orbital. That means that carbon ought to be sp2 or possibly sp1. I can't think of any of these yet. Maybe there's some we'll look at. The p orbitals must overlap continuously around the ring. Structure must be planar or close to planar for effective overlap to occur. So there might be some aromatic requirements. Got to be cyclic, conjugated, can't have any sp3 carbons in there, and a planar structure. That would be a paraphrased Cliff Notes version of these three things. Delocalization of the pi electrons over the ring must lower the electronic energy. Well, this is kind of an afterthought. How do we know when to apply number 4? So here's just a diene, cyclic diene, cyclohexene, diene, here's diene. We say these have similar stabilities, meaning they add Br and do those normal things. Why is this non-aromatic? Well, here's 2 sp3 hybridized carbons destroying everything. I imagine that might throw off some planarness. You can probably say it's not planar, and not every carbon is sp2 hybridized. And of course we can see that going on here. These are not sp3 hybridized. Of course this thing wobbles around and only looks like a ring in this conformation, as all those other conformations. Non-aromatic compounds do not have a continuous ring of overlapping p orbitals and may be non-planar. So here's this cyclobutadiene. Looks conjugated, looks planar, not very stable at all. We actually say it's less stable than this 1,3-butadiene, which we looked at so much in the last chapter. This you can put in a bottle, and it has probably a fairly long shelf life. Only if there's contaminants, some light, it can start undergoing polymerization reactions. So when something's less stable, we can call it anti-aromatic. Anti-aromatic compounds are cyclic and conjugated, and they have everything going for them. They got the overlapping p orbitals around the ring, but electron delocalization increases its electronic energy. So this is violating number 4 of that list, Hückel's rule. So those 3 criteria, once those are met, you get to apply this rule here. If the number of pi electrons equals this magic formula, 4n plus 2, the system is aromatic, where n is an integer. 0 an integer? I think so. So it can have like 2 or 6 or 10. You can just start putting in different values of n. If the number of pi electrons equals 4n, and let's just put some examples up here. I'm probably going to go 2, 4, 6. And then I can say, oh yeah, n equals 1. So I got 4 times 1 plus 2 equals 6. That's aromatic. If I come over here, I go 2, 4. I have 4 pi electrons. Can you plug any integer in here to get 4? I can plug in 1/2, but that's not an integer. So, but n equals, well, n must equal 1 here, making this equal 4 pi electrons. So that's how you apply this rule and this rule. You count these pi electrons, and it's either going to equal this expression or that expression. If the number of pi electrons is 4n, like it is with cyclobutadiene, then we say anti-aromatic. Benzene here fits this formula nicely, and we say it's aromatic, or number 4 on that list of criteria. This is how we know if the electronic energy is raised or lowered. This thing, it's lowered and things become aromatic. This thing here, they're increased and becomes anti-aromatic. Hückel's rule is commonly used to determine aromaticity and anti-aromaticity. A continuous planar ring of overlapping p orbitals is required for the rule to apply. Otherwise, the system is non-aromatic. This thing here is a tough one because when you see this drawing and the question says, is this aromatic or anti-aromatic? It's easy to look at this and say 2, 4, 6, 8. Well, 4n plus 2. I can't get 8 electrons out of that. Is it anti? Put a 2 in there. Well, the interesting thing about this is this flat representation in this board is really deceiving. It's deceiving in this almost looks like a 45 angle here. And if you think about the 120 all over, something's not quite right. But when you build the model, I think I took it out of my office because it's kind of big, but it forms this weird shape. They call it a tub. And you can see these pi bond, these unused p orbitals are going like this, and these are going like this, and they don't have that parallel overlap. So this looks planar. It has the criteria of every carbon is sp2 hybridized, but this cyclooctatetraene assumes a non-planar tub conformation that avoids most of the overlap between the adjacent pi bonds, and we simply can't apply Hückel's rule. I got ahead of myself, got all tangled up. I wanted to apply one of those rules. So this is neither aromatic or anti-aromatic. We just say it's what? Non-aromatic. It's not a binary thing. It's a tertiary thing, I guess. Got 3 options. So the cyclobutadiene is anti-aromatic. This 8-annuline, that's a whole lot easier to say than that real quickly, would be anti-aromatic, but it's not planar. I guess I should have worked a little longer. 2, 4, 6, 8. Yeah, n equals 2 into the 4n rule would make it anti-aromatic, but it's not planar. So it's just plainly non-aromatic. 10 annulines. 10-annuline is aromatic, except for the isomers that are non-planar. Non-planar. That must mean it has a trans bond somewhere in it, where normally we might think of these as all being cis. Larger 4n annulines are not aromatic because they are flexible enough to become non-planar. So what do I got going on here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is our 10-annuline. It is non-aromatic. Naphthalene is aromatic. 2, 4, 6, 8, 10. N equals 2. 4n plus 2, 10 electrons. This thing's aromatic. And so they're telling you here, here's 2 trans bonds, and it puckers up. I don't like the thing anyway, because these 2 things have different degrees of unsaturation. I don't want to try and compare them. But anyway, there you go. The 10-annuline isomer with 2 trans double bonds cannot adopt a planar conformation either because the 2 hydrogen atoms interfere with each other. So Hückel's rule, using a molecular orbital diagram, putting these electrons in, putting them in over here. Aromatic compounds have this 4n plus 2 electrons, and the orbitals are nicely filled. The anti-aromatic compounds have only 4n electrons and have unpaired electrons in 2 orbitals of the same energy, degenerate orbitals. So we want to play some fun games with cyclo. If you were asked, is this aromatic, anti-aromatic, or non-aromatic, what would you want to come up with? Well, on that first criteria, right here is a sp3 hybridized carbon, so I'd say don't even need to go to Hückel's rule with the 4N and 4N plus 2 business, I would just classify this as non-aromatic. Of course, I count 2 4 pi electrons. But what type of things can happen? If I pull off a hydride, I can get something that looks like this. That's a horrible drawing. If I do an acid base, pull that proton off with a strong base. So here's the anion, and here's the cation. And now they all have this continuous parallel p orbitals. The cation has an empty orbital and 4 pi electrons. So this thing is antiaromatic. The anion has a non-bonding pair of electrons in a p orbital for a total of 6 and is aromatic. So this is aromatic, this is anti-aromatic, this thing is neither. So this thing here to me is amazing. Here's our T-butoxide, our bulky base. Here's T-butyl alcohol. So this proton, these protons here are acidic enough for this thing to come pull a proton off, leaving a lone pair of electrons there. This must be the conjugate base of this acid. And we look at this alcohol and say, wow, the acid-base chemistry says this should happen. And of course, at this point, you say, well, of course it happens. You form an aromatic compound, and aromatic compounds have low energy. Because now I have my 2, 4, 6 pi electrons in a nice cyclic compound with all those overlapping, parallel overlapping p orbitals. If we deprotonate the sp3 carbon of cyclopentadiene, there will be a pair of electrons in one of the sp orbitals. This sp orbital can rehybridize into an sp2 orbital, leaving the lone pair in an atomic p orbital. Any questions?